Hi everyone, I'm Professor Burgasser, and in this video we're going to be talking about ways of solving statics problems. Just to remind you that a statics problem is a case where you have an object that's not accelerating, so the sum of the forces acting on the object are equal to 0. Keep in mind that doesn't mean the objects aren't moving, it just means they're not accelerating, their velocities are not changing. So there's a few steps that we'll follow and we'll illustrate in some of the examples we'll do in the next few segments. Just keep in mind the steps that we're looking at. The first step is to make sure we draw accurate force diagrams for all the important components of our problem, breaking down our problem into the interacting pieces and writing those force diagrams. Choosing a convenient coordinate system that applies to all of the objects and all of the force diagrams uniformly. Writing down our components of forces along the axes of those coordinate systems. And then writing down our equation of motion, which is really just the sum of the forces in each of the coordinates is equal to 0 for all of the objects, because if none of them are accelerating, that is a statics problem. We use those equations to solve for the unknowns, and then it's always important to go back and check to make sure our solution makes sense. So as our first example, let's consider something we've looked at before, holding something against a wall with just our finger and friction. Okay? So a question we might ask about this particular situation is, what's the minimum force that I have to apply with my finger in order to keep this book on the block, in this case, in the wall? So we can break this problem down again as a statics problem, because as the book is here, it's not moving. So all we need to do is start writing down our force diagrams and choose a convenient coordinate system, and we're on our way. So let's break down this problem into its relative parts, which is going to really be mostly the book. So let's just draw a force diagram over here for the book. All right, and now we have to start thinking about all the forces that are involved in this problem. Of course, this is a problem that's happening here on Earth, and so we have to include the weight of the book. The mass of the book is given as 0.5 kilograms, and so this is just equal to 0.5 kilograms times the gravitational acceleration near the surface of the Earth, and this gives us 4.9 newtons for the weight of the book. All right, now we have to look at our contact surfaces, and we've actually got a couple of them. We've got the surface in which the book is in contact with the wall here, and so we have to look at both the normal force and the friction force that are interacting between these two surfaces. So I've flipped my diagram a little bit, so let's draw with the wall here. All right, so I'm going to assume that the wall is right here. So in that case, the normal force is pointing away from that surface. And then the friction force between the book and the wall is going to point in the opposite direction in which the ball would slide if there was no friction, which would of course be downwards, and of course along the surface. And so there's a friction force between the wall and the book. Now that's not the only surface in play here. There's also the surface of my finger when I'm holding the book here. That is a surface that's in contact with the book, so we have to consider the forces that are acting at that surface as well at the contact point, which is both the normal force and the friction force in there. So our normal force is really the applied force that we're applying the book to keep it here, so we're going to call that just capital F. And now we've got to take into consideration that there's also some friction acting between my finger and the book. So there's another component of friction, and again, if there was no friction between my finger and the book would just slide and we'd have no friction there. And so there's going to be a friction component that's pointing up, that's between the book and my finger. Now, we have an expression for these friction forces. All right, they're equal to mu times the normal force being the force at contact that's perpendicular to the surface. And so for the wall force, this is going to be mu times our wall book coefficient of friction, which I've written down over here, just flip the words around, it's 0.4, times the normal force, which is our Fn, and the friction between the book and my finger is equal to the coefficient of friction between my finger and the book, which I've estimated to be about 0.3, times the normal force, but the normal force in this case is the force that's acting between my finger and the book. It's not the normal force from the block, so that's just equal to F. Okay, so now we've gotten all our forces together, and fortunately they're written in such a way that there's a very convenient coordinate system if we just choose our coordinates to be x hat and y hat, rectangular coordinate system, all our vectors line up with that, and so we don't have to do much in terms of breaking down the components. We can just start to solve the equations. So let's look at the y hat component, actually, so let's look at the x hat component first. All right. So there's only two forces acting in the x hat component. There's the there's the applied force F, which is acting in the positive direction, and the normal force from the wall that's going the opposite direction. And since it's a statics problem, that's equal to 0. And so we immediately get a relationship between the normal force and the applied force. They're equal to each other. Easy. Let's look at the y direction. All right. So again, looking at the way I've written my vectors, we've got the friction force between my finger and the book. So I'm going to just write that out explicitly. Mu Fb times the applied force F. We've got the friction between the wall and the book, which is mu Wb times the normal force, Fn. And see if I have a problem with my notation. So this is generally equal to a normal force, so just make sure that's clear. And then we have 1/5 force, which is the weight pointing down. That's just equal to minus mass of the book times g, which we've already figured out to be 4.9 newtons. And that also has to equal 0 because we have a statics problem. Well, we've already solved that the normal force and the applied force are the same, so we can rearrange this around to write that mu Fb plus mu Wb times the applied force is equal to mg. And we can write down now the force is equal to mg, which we figured out is 4.9 newtons, divided by the sum of the friction coefficients, which is 0.7. And that's just equal to 7.0 newtons. And that's our problem, or that's our solution to our problem. Now, it's interesting to point out that that 7 newtons is actually much larger than the force if I just held this book. Right? The applied force for just holding this book is just our 4.9 newtons because it's just the weight of the book. So this is not a particularly efficient way of holding a book up, and I do have to push a little bit harder to keep this book here. And so that makes sense for a solution that we get a bigger number for the applied force than the actual weight of the book. So let's do another example that involves tension as a force. Again, a statics problem with wires in this case, looking at something that is perhaps suspended by a complex system of wires. This is not too complex, we're going to keep it simple. So let's say we have a mass of about 10 kilograms that's suspended from this system of wires. We've got two coming out from two blocks. They're connected at a middle point, and then you have a suspended wire that goes down. This may be how something is suspended from a bridge, for example, or a signpost. So one of the questions we might ask about this system is which one of these wires is under the most tension, because that will allow us to predict where we might have a break in the wire. What are the wires that are under the most stress, and how we could relieve that stress. So again, this is a statics problem, so we can dive right into starting to draw our force diagrams. We've got a couple places, but let's start with the obvious one, which is the mass that's suspended there. All right. This being a problem close to the surface of the Earth, we're going to have a weight on this object. Fw, that's just mass times gravity, and that's equal to 10 kilograms times 9.8 meters per second squared, or 98 newtons pointed downwards. Okay, now we can look at the contact forces. In this case, we're talking about contacts with wires. And remember that tension in wires or strings are always going to point into the string or wire and along the string of wire. Wires don't pull sort of sideways. They always connect right up to their connection point. So that wire connection there, we're going to just draw a tension force. And I'm going to call that the force of tension for wire number 3. So in fact, since we're going to ask a question about different wires, let's go ahead and label these wires. This is going to be number 3. This is going to be number 1. This is going to be number 2. Okay. And that's it. There's no other forces acting on this particular mass. So now where else can we consider forces? Well, we've got this connecting point between these different wires, and that point is also not going to move. It's a statics problem. So we can assume that there's going to be a force balance at that point as well. So let's take a look at what's happening at the forces there. So I'm just going to draw that point down here and look at the forces acting. Well, we've got the equal and opposite reaction force, the wire pulling on the block. That tension is going to run across the entire wire, so that same tension force is pulling down from this point. So this is our FT3. And then we've got two other wires that are connected to these points, so I can draw in those tensions as well. FT1 and FT2. All right? And again, there's no other forces, and so this is kind of the sum total. Now I can also look at the forces acting up at the top, but as we'll see, these are sort of the minimum pieces that I need to look at in order to solve this problem. Well, now I got to choose a convenient coordinate system, and we've got angled vectors now, so it's probably just easiest to choose a coordinate system that's lined up with our gravity vector. So I'm going to choose this to be x hat and y hat. Right? That applies to both force diagrams. So now I've got to take this force diagram and break it down to the component parts. And this is going to now involve a little geometry. So the first force vector is p sub k because it's pointed along the y-axis. But how do we break up these components? Well, we got to go back to our diagram and look at the geometry of the system. So I've given a few lengths here. The length of these wires is 2.1 meters. And the separation between their connecting points is about 4 meters. Well, we can fairly easily draw a nice little triangle if we divide up this section here. And I'm going to call this angle theta. And let's take a look and see what that angle theta is. So this angle here is, we've got two sides that are known, the hypotenuse. And keep in mind this is a right triangle. So this is the hypotenuse. And we've got to measure for the opposite side, which is half 4 meters, 2 meters on the side. So we can compute what sine theta is. Sine theta is the opposite over the hypotenuse. This is 2 meters divided by 2.1 meters. And when you calculate all that out, you're going to get 72.2 degrees. And notice I've kept an extra significant digit because this is not my final answer. I'm going to keep that just to keep my precision as accurate as possible. Okay, so now how does that angle translate into the geometry of these vectors? Well, that angle factors in because if I draw the same vertical here, that is just this angle right here. So I can compute my vectors along those coordinates using the angle I've just calculated. There's going to be a component of FT2 that is parallel in my coordinate system. And if we look at the way to define my angle, that's going to be the opposite side of the angle. So this is going to be sine theta. And of course the other component is FT2 times cosine theta. And the FT1 is exactly the same, just in the opposite direction along the x-axis, but the trigonometric functions are the same, times cosine theta. A little bit tiny writing, but you get the point. Okay, now one last observation we can make about this is the way the geometry of the system is set up, it's very symmetric about the middle of the diagram. So I would suspect that the tensions on either side of these are going to be the same. So we can make a simplifying assumption that because of the symmetry, tension 1, force of tension 1, is going to be equal to the force of tension 2. So I really only have to calculate one force that's going to be the same for both of those components. Okay, so let's now take our forces that are broken up into these components and write down the equations of motion along our axes. The first place I'm going to look at is I'm just going to take this one diagram because there's only one dimension I have to worry about. So let's look at block number 3, and that's along the y-axis. And we get a very simple equation that the tension force 3 minus our weight is equal to 0 because it is a statics problem. So that just gives us an expression for our tension force 3, which is just the weight, which is just equal to 98 newtons, already solved. Okay, so now let's take a look at, so we can do a couple different axes for the next force diagram. I've already said that the tension forces along both sides are equal to the same thing. In fact, we could have actually solved that from this force diagram, because notice that along the x-axis we have ft1 sine theta pointing in this direction, ft2 sine theta pointing in that direction. Those sum up to 0, so they have to be equal, right? Those magnitudes have to be equal. So now let's look at these components where there's actually 3 vectors, because there's 2 from the 2 tension components. So let's look at the connector points. So this is 1 and 2 along the y-hat direction. All right, we've got ft1, and that's 1, 2, they're the same, times cosine theta. And we've actually got 2 of those pointed up. And then we've got minus ft3, but ft3 is just our weight vector. We've already figured that out to be 98 newtons. And the sum of that is also equal to 0. All right, so now we can solve for the tension force in both the 1 and 2 wires. That's just 98 newtons divided by 2 times a cosine of 72.2 degrees, which turns out to be equal to 0.31. And when we write all these numbers out, we get a tension of 160 newtons, 2 are significant digits, for each of the tension forces in the wire. So we can immediately discern that the wires under the most tension are these 2 right here. They have almost twice as much tension in them as the little wire that's connected to the mass itself. Now, this is also where you can start to think about how can we reduce the tension in the wire. We've divided by cosine theta, and theta was a very steep angle because these wires are apart quite strongly. If I make this angle smaller by reducing the distance between those 2 blocks, so if I bring these together, that's going to make a smaller theta, which is going to make a larger cosine theta, which is going to divide out and make a smaller tension force. So based on our expression, we can actually come up with a way of reducing the tension on these wires based on the geometry. So let's look at another tension statics problem, in this case using pulley systems. What I've diagrammed here is an example of a gun tackle pulley system. It consists of 2 pulley wheels with a mass connected to the bottom one. The string or the rope that's holding this up runs through the top of the pulley wheel, then through the bottom one, and then it connects up to the middle of the support structure for the first pulley wheel, and again the mass is connected down to the bottom one. So a perfectly valid question to ask for this kind of system is, how much force do I have to apply? How hard do I have to pull in order to keep this mass of 40 kilograms off the ground? This may look like a very complicated system, but in fact if we break it down by its forces, you'll see that it's actually not that hard to solve. So let's take these pieces one at a time. Let's start with the mass at the bottom here, this 40 kilogram block. Right? We are near the surface of the Earth, and so there's going to be a weight component to that, which points down. That's just its mass times gravity. Its mass is 40 kilograms, and surface gravity is 9.8 meters per second squared. So when you write that all out, you get 340 newtons. The other force to consider is the contact of the string that's holding that weight up to the mass itself. And so we can write that as a tension force that's holding the block up. In fact, I will label it as the block of the tension. So now let's look at the next piece connected to that, which is the bottom pulley wheel. So I'm going to draw a little representation of that over here. And we can start by looking at the mass, again, of the pulley wheel, in which case we've actually given this pulley wheel a mass of 2 kilograms. So that's going to be a weight that it holds down, right? That's also equal to its mass times gravity, which in this case is going to be 2 kilograms times 9.8 meters per second squared. That gives us a value of about 20 newtons. Now we can also look at the action-reaction pair for this tension force that's holding this block on. That tension runs across the whole rope, and it's also attached to the pulley, and it's going to pull down because it goes towards the string. So we've got a second downward force, which is our tension that goes to the block. We've also got the string connected up to the sides here, And one thing, if you remember from pulley systems, is that as long as we have an essentially massless or close to massless string, the tension at any point along the string is going to be constant. And so where the string connects up to the pulley wheel is going to pull with the same forces as we're pulling over here on the side. So those are then easy to draw in. We've got a sort of vertical force pointing here. On this side, the force is kind of a little bit toward the angle, but just for simplicity's sake, I'm going to assume that it's pretty close to vertical at that point. So we've actually got two tension forces from how hard I'm pulling. They're acting on either side of this pulley. And that's it. There's no other connection that are making contact with that bottom pulley. So let's start with these two diagrams. And notice that they are nicely aligned. In fact, it's a one-dimensional problem, so this is one of the easier ones, right? So I'm just going to choose a single coordinate axis that points up. And that's the only one that I have to actually solve. So let's start with the block y hat equation. So we've got our tension force between the block and the pulley that's pointing up. And then we've got our minus the weight, which is just m times g. And that's got to equal 0 because this is a statics problem. And so we immediately figure out that the tension force on this rope here is just equal to the weight of the block, and that's equal to 340 newtons. All right. Now let's look at the pulley, again in the y direction. All right. Now we've got two components of force, 2 times F pointed upwards. Then we've got our tension from the block pointing downwards, but we've actually already solved that. That's 340 newtons. And we've got the actual weight of the block that's applied. That's another 20 newtons that we've got to subtract off. And that whole thing equals 0 as well. And now you see we've actually come to the solution because all we have to do is write these two numbers off to the side. So this is going to take a 360 over that side. We divide by 2. When what we get out is the tension force applied is 180 newtons. Now it's important to think about this solution a little bit because the weight of the block is 340 newtons. So by putting this in this pulley system, even though the pulleys themselves have mass, we kind of have to hold those up as well. We've reduced the force load on the object almost by a factor of 2. And that's pretty common for these pulley systems. For every wrap that you have, you reduce another factor of the weight of the object you're trying to lift up. Now the trade-off, of course, is if you're trying to lift this up, you can't lift it up as quickly because you're wrapping this rope up as you're moving this thing around. So it's easier to hold up, and of course it's easier to pull it at a constant velocity because that's exactly the same force, but it's going to be a much slower process. But this explains why pulleys are such useful items when you're actually trying to lift very heavy things. So we've seen a few examples of statics problems, and hopefully you remember how to set up the problem so you can solve all sorts of different variations. But the main steps are looking at your system, setting up the force diagrams for all the important components. All right, so we have some examples of that here. And applying all the forces, just as we've done looking at different force diagrams, making sure you go through your system of forces and that they're all on our diagrams. Then we want to choose a coordinate system that's convenient for the problem and break down the forces in our systems into those coordinate systems. And then we can just write down the equations of motion because that's just the sum of forces along all the axes is equal to 0. These are the equations I wrote down here. And then you go about solving for unknowns. And then of course the most important step is then to evaluate your answer. Does it make sense? And is there anything unusual that you can discern by looking at the patterns in that problem? So good luck with your statics problems.